It's plus K, isn't it?
It's
what? It's plus K.
That's the K, yeah. It's a very ugly looking K. Okay, so this is basically vertex form. The A does two things. If A is negative, what does it cause? Reflection. If A is a number other than 1, then it's either going to cause a vertical stretch or a vertical compression. If it's greater than 1, it's a vertical stretch. If it's less than 1, it's a vertical compression. Okay, the H and K cause shifts. H would cause a shift left or right. K would cause a shift up or down. So what we're going to look at today is, what if there's something inside here? Okay? So whenever anything is grouped with our X, it causes a horizontal change. If it's added or subtracted to our X, that causes a shift, like the H does. But if it's multiplied times our X, that causes a horizontal stretch or compression. Now, just like we always do the opposite of this, we always do the opposite of what's grouped with our X, when we have something multiplied inside there, we do the opposite of this. So the opposite of what's multiplied in there causes a horizontal stretch or compression. So when B is greater than 1, it's kind of the opposite. We think that would be stretch, but what's the opposite of stretch? Compression. And when that B is between 0 and 1, it actually causes a stretch. Now, I read all the little silly comics on Facebook, so I know when I use letters in math, it doesn't make any sense. All my adult friends talk about how dumb math is on Facebook. And I feel for them, and I would like to offer them tutoring sessions. All right, but here we go. So, we have something inside the parentheses multiplied times X. Now, it looks like it ought to be a horizontal stretch, but it's really a horizontal compression. So we have to do the opposite. What this causes is a horizontal compression by a factor of, what is the opposite of multiplying by 2? What has the opposite effect? Dividing by 2 or multiplying by a half. So that's a horizontal compression by a factor of 1/2. Look like your eyes.
I just rubbed them.
Okay. All right, so here we go. So what would that cause?
Compression by a factor of 1/5.
A horizontal compression by a factor of 1/5. Okay? No, actually they're not. It looks a little frightening, but it's not. All right. Now this one's times 1/3.
By 3.
Very good. So if we think, what is the opposite of multiplying by 1/3? Multiplying by 3. So this is going to cause a horizontal stretch by a factor of 3. Or if we write it like this.
By 4.
Isn't x divided by 4 the same as x times 1/4? Could I write those? Aren't those the same? Yeah. So this also causes a horizontal stretch because the opposite of dividing by 4 is multiplying by 4. Okay. Today, the only thing we're going to do to earn our points for the day is take notes, and it appears that everybody's actually doing that, so that's awesome.
Of course, Miss Lynn.
Yes, of course.
Perfect children.
Always.
Always they do this.
That's right. Okay.
4 years.
So now that we know how to explain in words what's going on, let's see what these same four are going to look like. Let's see what they're going to look like. That first one is not a bad one at all. Y equals 2x squared. Okay, so I have started with ones that are not shifted in any way, shape, or form. So when they're not shifted, where's the vertex?
0, 0.
At the origin. 0, 0. 0, 0. Okay? So, yeah, we're going to go back and graph this horizontal compression one. So you can just write 1 again and just, you don't have to write horizontal compression again. You ready? Okay. So, we know our normal moves are plus or minus 1 squared is 1. Plus or minus 2 squared is 4. Right? And the left side represents our left and right, horizontal. The right side represents our up or down, our vertical. Now, we have changed something here. We have changed the horizontal.
Divide by.
So what we have to do is we have to go in and take those horizontal moves and multiply them by 1/2.
Do the y stay the
By
same?
1/2. And this time, the y's don't change.
Okay.
So this becomes plus or minus 1/2, 1. What is half of 2?
1.
Very good. Plus or minus 1, 4. So we go over 1/2 up 1. Over 1 up 4. Over 1/2 up 1. Over 1 up 4. Okay. Does it look like, and let me draw in the original, y equals x squared. Here's our parent graph. Does it look like I took this parent and horizontally compressed it? Swoosh. Does it look like it's been squished?
See.
Yeah. That's a horizontal compression. Like we took it and pushed it in on the sides. Pushed it in horizontally.
Put it in
Now,
put it in
The
trash compactor.
interesting thing about
Put it in
this
trash compactor.
is there's actually 2 ways we could describe this. Horizontal compression by a factor of 1/2 is the way the equation is written. But guys, can't I square stuff that's in parentheses? What happens if I square that too?
4.
It equals 4. What happens if I square the x? It is x squared. Do you see that a horizontal compression by a factor of 1/2 is the same as a vertical stretch by 4?
So could you do that?
Yes.
Just
So
switch it to
if you
vertical?
don't like horizontals, switch it to vertical. Let's see if this truly works. If I treated it like a vertical. Okay, you guys need to separate today because we're really struggling to pay attention. Okay? So why don't one of you come sit in those 2 desks and one of you come sit here. Whoever gets up first can get that desk. Whoever gets up second can come sit here. All right.
sitting?
Right over there. All right, so vertical stretch by a factor of 4 times by 4 times by 4. Do you guys see the point 1, 4 is on that pink graph? Negative 1, 4 is on the pink graph. So this vertical stretch is the same as the horizontal compression.
You just skip the points.
Yeah. You won't get the in-between points, but all the dots that you get by plugging in here, if we plugged in 1/2, it would give us that little pink point right there. It would be there. Okay. So that's the interesting thing about horizontals. Now, I'll go ahead and be honest with you. We can make horizontal stretches and compressions really ugly. We're choosing not to.
Okay.
Okay? So, as a math department, we've decided to keep the horizontals pretty basic. But later on, when you get to trig, you'll see that the horizontal stretches and compressions really do play a big role in the waves when we get to sine and cosine, and then we'll do more with them. But right now we're sticking with easy basic ones, because we could, nobody write this down, everybody put your pencils down because I don't want you to do this. We could give you questions like this. Where we have to factor out
The inside.
the horizontal on the inside. And we have a horizontal and a vertical. We're not doing that. We're not going to do that. But eventually when we get to trig, these horizontals will come back and they'll matter then. So since it doesn't matter now, we're not spending our time doing it. Okay? Alright, so we're going to focus on the kinds that we are going to be doing. And let's take a look at the next one. The next one is one that would be a pain to graph. It's y equals 5x squared. So, if you like rewriting it as a vertical and graphing it that way, because what is 5 squared?
25.
25. So a vertical compression by a factor of 1/5 is the same, a horizontal compression by a factor of 1/5 is the same as a vertical stretch by 25. Now, this would be ugly to graph, wouldn't it?
C.
The only way I would graph this, I would probably, it's just ugly. Because if we go over 1, we have to go up 25. So we're going to skip graphing that one, and we're going to graph the next one. The next one we did was y equals 1/3 x squared. Okay, I'm going to graph this like it's horizontal, because that's actually the best way to graph this one. Okay, did I do any shifting at all?
No.
No. Okay, my vertex is right here. So we said just a second ago, we think the opposite of 1/3. This is a horizontal stretch by a factor of 3. Because the opposite of multiplying by a third is multiplying by 3. So if we think about our moves, plus or minus 1, 1, plus or minus 2, 4. We take and multiply these horizontal moves by 3. 3. So I go right 3 up 1, left 3 up 1, right 6 up 4, left 6 up 4. Now, so how would we make this look the same if I did it as a vertical stretch? As a vertical stretch, this is 1/9 x squared. So if we did plus or minus 1, we're going to get 1 times a 9. That's a little difficult to graph. If we did plus or minus 2, we get 4 times a 9. So if I went left or right 2, does it kind of look like I went about a half, 4/9?
Yeah.
Sort of. Plus or minus 3 is 9, isn't it? What's 9 times a 9? 9 times a 9 is 1. So did I go 3, 1, 3, 1? So you see how either way you think about it, you get the same graph. But this one's actually easier to do as a horizontal stretch. The horizontal stretches are easier to do as a stretch than a vertical. Okay, And the last one we did without any shifting is y equals x over 4 squared. So I want you to try to graph this one as a horizontal stretch. So this is a U try. You're graphing this one as a horizontal stretch. It's a horizontal stretch, we said just a minute ago, by a factor of 4. All right. Got this? Awesome. Okay, so normal moves are plus or minus 1, 1, plus or minus 2, 4. But this is horizontal. Horizontal multiplies the x's. So I go plus or minus 4, 1, plus or minus 8, 4. So from this vertex, here at 0, 0, I'm going to go right 4, up 1, left 4, up 1, right 8, up 4, left 8, up 4. I'm off my graph, but you kind of get the idea. Whee! Does this one look like, if I drew in the parent graph, y equals x squared, I'm going to do it in green right here. Does it look like it's been pulled horizontally, stretched out this way, pulled horizontally? That's why we call it a horizontal stretch, because if I can grab hold to the ends and pull them out, it gets me that new function. It's a horizontal stretch. We get it? All right. So now let's do a couple that have a vertical shift to them. Oh, I want to talk about one more thing. What would happen if I put a negative in here? If I put a negative inside the parentheses, it's a reflection across the y. It changes all the x's to the opposite. Well, because a quadratic is symmetric, if I flipped it like this, does it look any different? No. If I reflect it horizontally, it looks identical. It reflected onto itself. Now, if I reflect it vertically, if I reflect it over the x-axis, it looks different. One opens up, one opens down. But when we reflect it horizontally, so if that negative is inside here, it looks exactly the same. Because what happens when you square a negative? It becomes positive. So it makes no change in the y values at all. So you guys really won't see this either. A reflection here, it just looks like itself. This 4, 1 would become negative 4, 1. And the negative 4, 1 would become positive 4, 1. And those points are symmetric across the axis of symmetry. And it looks exactly the same. All right. So we shouldn't see that, but I did want to point that out. Okay, let's do a couple that have a vertical shift to them. Okay, the only difference, and this one and the last 4 that we've done, is instead of starting at the origin, where do I start?
Negative 4.
At negative 4. That's the only difference. Okay. So, put my little graph on here, and we're going to start at negative 4. All right. Is this a horizontal stretch or compression?
Stretch.
It is. It's a horizontal stretch by a factor of what? 2. So that means I take those x's and they get multiplied by 2. 2. So I actually go plus or minus 2, 1, and plus or minus 4, 4. 2, 1, 4, 4. 2, 1, 4, 4. Okay, I'm going to give you 3 to try, and I'm going to put student work up on the, what do you call that thing? My document camera. Document camera, that's what we call it. So, I'm going to give you 3 to try. You can talk to each other. You can ask me questions. You can ask Miss Goodrich, and then we're going to put these up, and that's going to be our practice for today.